star interactions with a supermassive black hole.
Hello, everyone. My name is Megha, and I'm third year PhD student at Monash University. And I'm working with Professor Daniel Price and Alexander Higa. Today, I will be talking about a benchmark for the binary star interaction with a supermassive black hole. So, three-body problem, it has garnered a lot of attention, even among the general public, as is evident from the Netflix show of the same name called Three-Body Problem. Uh, can you hear me clearly?
Yes.
Okay. Um, and we also tried to solve a three-body problem, which involves a supermassive black hole with a binary star system. So why do we care? Well, most galaxies have supermassive black holes in their centers surrounded by stars. Um, and our own galaxy is also home to a supermassive black hole of 1 million solar masses. So we wanted to understand how a binary star would interact with the supermassive black hole. And this is a hard problem to solve because you also need to consider general relativistic effects. So to solve this problem, you would usually want to use um, the numerical general relativity, but it's very expensive and very hard. So instead, there are two different methods to do this problem. One is using post-Newtonian correction terms, which is also being done in the code known as Tsunami. And we are using a different code called Multistar, which has been written by my supervisor, Alexander Higa. And the other way to solve this problem is to use a Newtonian perturbation to the metric. And we use two different codes for that as well. We use Phantom Geo, which is an updated version of the geodesic code that was written by David Liptai and Daniel Price in 2019. And the other code we used is called HMRA, which has been written by msun, and the paper was published in last year about the implementation. So in post-Newtonian codes, we basically add correction to the Newtonian gravitational force of the order of v by c squared. And it's only accurate when the velocity is much smaller than the speed of light. It assumes weak field near the black hole. And the way both the codes that we are using for post-Newtonian physics work is that they implement the post-Newtonian terms in a pairwise manner to the three-body problem. And then the other codes we used is for the metric with a Newtonian perturbation. And the phantom geocode basically solves this change in momentum equation. Um, Instead of just having the metric, we also have now a perturbation term, which results in the equation having additional two terms, as you can see here. And we ignore the third term because it's of the order of v squared by c squared. And we also assume that u naught is 1 for our calculation. In Harna, they start with a geodesic equation and they consider the Newtonian perturbation as well. And they derive this equation for the change in velocity. And it already has the u naught term in there, as you can see. So we did two different tests to see if these four different codes match with each other or not. This test one is for 1 million solar mass black hole, and we show set 0.5 solar mass stars at a distance of 50 times the tidal radius. So tidal radius is basically the distance at which the gravitational force of the black hole will basically overcome the binary's self-interaction force. And we set them all at a distance of 50 RT. This model was taken from a paper that was published last year for the code HERNA. And in the first panel, we just show the model that we run in the phantom geocode. We can see that the star one gets unbound, gets bound, and the star two gets unbound. And all these simulations are being run for 1 year in these results. The second one shows the comparison with the other GR code, which has a Newtonian perturbation. And we can see that they match pretty well with a difference of about 1%. And then in the third panel, we compare the phantom geocode with the multi-star, which is the PN code. And now we can see there is difference. So we plot the first order post-Newtonian term and the second order post-Newtonian term here. So the 2PN includes the 1PN term as well. And we can see that 1PN term is not very good match with what we expect from the phantom geocodes. But if we add the higher order post-Newtonian correction terms, the precession and the way the star's orbit is inclined kind of matches well with what we expect from the phantom geo and HRNA codes. But still, the precession is faster in the multi-star code compared with the GR with the metric codes. And the fourth panel shows the comparison between the two PN codes. And we can see that they match really well again with the difference of about 1%. Here we have also included 3.5 PN terms. So the second test we ran was for a much higher black hole mass of about 10 to the 9 solar masses. Um, it's actually, we used 1 solar mass, not 0.5. This is wrong. And we have a ratio of the tidal radius to the pericenter distance of 0.1, which means that this in basically pericenter would be much would be quite far from the tidal radius. And we can see it in these models, we set all of them at a distance of 1,000 tidal radii at the beginning. And the first panel again shows the phantom geocode. The stars get close to the black hole and they get split apart. In the second case, we show the comparison with HRNA. And we can see that even though we ran the same models for the same amount of time, which is 4.5 years, there is clearly a difference in the way the binaries are behaving. Then we compared the phantom geocode with the multi-star in the third panel. And again, we can see there is difference. And the fourth panel shows that multi-star and tsunami match well with each other, which means that PN codes are working similarly, but there is still some discrepancy between the GR codes. So this plot here shows the separation between the binary as a function of time. The first panel shows the multi-star versus tsunami. So basically only comparing the post-Newtonian codes, we see that there is some sort of shrinking that takes place in this system. Even though the system stays circular, if we look at the eccentricity versus time plot. We are still not sure why this is happening. And then the second panel shows the multi-star versus phantom geo with HRNA. And we can see that both HRNA and phantom geo show similar behavior where the models become highly eccentric and the separation decreases a lot. But the time at which this happens is about a year earlier in the phantom geo compared to HRNA. So why is this behavior taking place? So for the PN codes, one explanation could be that we are using pairwise implementation of two-body PN terms in a three-body system, which is resulting in this shrinking of the orbit behavior, even though the system stays circular. For the difference between the phantom geo and the HRNA codes, as I mentioned earlier, we had simplified our equation for phantom geo, where we had ignored the V by C square term and used G naught as 1. We basically put those back in and reran the model, and we found that they actually still behave pretty much the same way, though. So basically, we still get the separation decreasing about about a year earlier than the other code, which is HRNA. And we also found that the energy conservation is not very good in either HRNA or use all these correction terms in phantom geo. But the energy conservation is good when we use G naught, U naught of 1 and we ignore the V by C square terms. So what would this have an effect on? So what I'm currently trying to do is to get collision statistics around different black hole masses. And this would clearly have an effect on it if I'm using the post-Newtonian codes, because at at small distances, further distances from the black hole, I could still have these collisions taking place because of this feature of the physics that's being used to solve the 3-point problem. So in conclusion, we compared 4 different codes, 2 post-Newtonian and 2 metric with perturbations, and we find they agree pretty well for the 10 to the 6 solar mass black hole. But for 10 to the 9 solar mass black hole, there is discrepancy, and we see this shrinking of the orbits, which takes place in almost all these codes, but the model becomes eccentric in the metric with perturbation code, but it stays circular in the PN codes. Yeah, thank you.
Megha, has anybody got questions for Megha? I'd like to start, Megha. You mentioned that the energy conservation is not so good under some circumstances. Can you elaborate on that, please?
Yeah, so energy and angular momentum. So we see that for the cases where we use all the terms in this equation, so use U0 and the third term as well, we don't conserve angular momentum well, and the same happens with energy too. And it's the same for HERNA as well. So even their energy conservation and momentum conservation is not very good for the problem, the second test that we did.
Okay. And I'll ask a second question. Which version should we use? If we're going to be doing this kind of problem, which version do you recommend?
I think both have their limitations, and we still don't know which one's correct technically. Yeah. But
Okay.
yeah.
Sorry, could you repeat that? I didn't catch that.
Oh, we are still not sure which one's the correct formulation to use. Yeah, because both of them have results which we still can't explain properly.
Yep. Okay. All right. Thank you very much, Megha. It was a very nice talk. We get our next speaker up.